Shelby, will you shut that door? Please, thank you. Okay, see, did we finish the clicker questions for this chapter? We did not. Where did we leave off? Anybody? 521A? We were almost done, right? Ooh. Did we do this one? No, I just showed y'all the answer, but that's okay, we'll do it. Trying to figure out the light. How's that? Is that okay? How about that? Is that okay? Okay, Mike applied 10 degrees force over 3 meters in 10 seconds. Joe does the same in 1 minute. Who did more work? Let's stop at 55 or a minute. We'll go to a minute. Just a few more seconds. What? Wait. Okay. I can go now? Okay. Okay, good. C is right. They both apply the same force over the same displacement. The time doesn't really matter when you're talking about work. That's only important when you're talking about power. Remember, power is work over time. How about this one? All right, let's stop at 45. 45. Okay, B is right. Joe, even though he does less work, he does more power. The work for Mike is equal to 5 over 10. The work for Joe is equal to 3 over 5. So this is, 0.5 and this is 0.6 watts. So Joe does more. He has more power expended in that amount of time. All right, let's stop at 35. 35. Okay, good. B is right. Just because it produces twice, or it has twice the power, doesn't mean that it does twice as much work. That it depends how long it goes, right? Is it chilly in here? Is it cool? If you ever get cold in this room, what you have to do, you can just stand right over here, like right over here in the corner. And every time you'll warm up. It's like 90 degrees over here. Yeah, at the right angle, it's 90 degrees. Okay, when you pay, I think this was actually, was this on your OpenStax, this question about kilowatt hours? It was? Kilowatt hours? Okay, so when you're paying by the kilowatt hour, what is it that you're paying for? Is that a measure of energy, power, current, voltage, or none of these? Think about what a kilowatt hour is. It's a kilowatt, which is just 1,000 watts, times an hour, which is a measure of time. So if I multiply power and time, what do I get? All right, let's stop at 58. 58. Okay, good. It's energy, because kilowatt, remember, or a watt is a measure of energy per time. And then when I multiply that by an hour, which is a measure of time, then it leaves me with just energy. So a kilowatt hour, that's in basic SI units would be joules per second times seconds. That would be equal to a joule. Right, because a watt is a joule per second. An hour we could convert to seconds, and it would just leave us with joules. Kilowatt hours is a measure of energy, not power. In fact, they don't really care what your power consumption is. Right? They don't care if you use all of your energy on a day one and then turn off everything thereafter. Okay, which contributes more to your electric bill, hair dryer or a 600 watt microwave oven? By the way, the hair dryer is like one of the biggest energy consumers in your house. And next time, think about that. I think about it every morning when I'm drying my hair, because it takes like a half an hour. All right, let's stop at 43. 43. Okay, good. It is E. It depends how long each one is on. So if you leave the 600 watt microwave oven on for 2 hours, but this is only for 30 minutes, then this is going to use more energy. Because that energy is power times time. It's not just the power of the device, but also how long you use the device. We'll see that again next semester when we do electricity. We get pretty deep into all that. All right, I want to work through a few problems in some of the old tests, but first, are there any issues with the OpenStax? Because it is due... Is it due tonight? Yes, it is due tonight. Any issues or things that y'all want to talk about? Particular problems? Look, I do want you to be careful. There was one problem where you had an inclined plane, and there was like a guy pushing a block or something up that inclined plane, and they give you this angle, theta. I don't remember what this angle was, but they ask you what is the work that's done by this guy, and what's the total work done in order to get the guy and the block up the inclined plane. Y'all know what to do in that case? How to approach that problem? This problem was on there, right? Yeah. So it was probably one of the more difficult problems. You need to go back a little bit to your inclined planes. And remember, well, first of all, we'll just treat this whole thing as one piece. So it's the guy and the block, and whatever the total mass is. And then realize that there is a force that acts down the inclined plane. And that force is equal to Fw times the cosine of 90 minus theta. And so that's the force that you're pushing up against. And so you have to provide a force that's actually opposite that. That's also Fw cosine of 90 minus theta. That's going to be the force that does the work, and then you just multiply it times the distance in order to find out the work that's being done. Okay? Does that follow? Yeah? Listen, I'm around this afternoon if y'all have issues, but I can help you if you've made a concerted effort and you want me to check over some of your stuff. I'm willing to do that. But if there are questions now, I'll answer them too. Y'all found it okay? The assignment? Yeah. I didn't want it to be too easy, but I tried to make it easier than some of the previous ones. Everybody's okay there? Okay, good. Well, let's work through some other problems. Let's see, let's do this number 2 here. This is on exam 3 from last year, number 2. What is the speed of the card at point B? I have this card up here. I want to know what is the speed here. You'll certainly see a problem like this on the test. Where that is. If you finish number 2, go on and do 7, and then you can also do 5. 2, 7, and 5. But right now we're taking answers for number 2. All right, let's go about 10 more seconds. Stop at 2 minutes. Okay, we'll go to 205. 205. 205. Okay, let's see. I think A is right. Let's just double check that. So when I do this, I want to say the energy up here is equal to the energy down here. And then also notice that it has a speed up here. So it has both kinetic and potential. So that's going to be 1/2 mv squared plus mgh is going to equal to 1/2 mv squared at the bottom, because down here the potential energy is equal to 0. All right? So I could write out this mgh over here, but it's going to be 0 at the bottom. I can get rid of my masses. They all cancel out. And I have 1/2 of 4 squared plus 10 times 10, that's 100, equals 1/2 of v squared. That's 808, 216, square root of 216. Yeah, that's about 15. It was A, right? Yeah, 14 point something. Okay. So let's do number 5 here. I'll try number 5. If I double the velocity or the speed, what happens to the kinetic energy? All right, let's stop at, say, 45. Look at that. Y'all are awesome. C is the right answer. Kinetic energy is 1/2 mv squared. If I double this, which is what I'm doing, then I'm going to quadruple, because it's that quadratic relationship. So C is the right answer. I went to the bank the other day. I just wanted to check sort of how much money we had. So I went up to the cashier, or the teller or whatever, I asked them, I said, hey, can you check my balance for me? She pushed me. Did y'all hear that in the back? Because you're not laughing. Okay. All right, which one did I say again we'd do? 7, right? All right, try number 7. This one's very similar to the roller coaster problem we just did, but you have a spring. I'll remind you that the potential energy of a spring is 1/2 kx squared. Alrighty. Stop in about 15 seconds. Feel free to share your answer with your neighbors. We'll stop at 150. Alright, good. A is the right answer. What you have here is you have a ball that's moving in this direction, and then you have a spring. And initially, all the kinetic energy is here, and the potential energy is equal to 0. But then, the ball compresses this spring, and so it stops. It has no kinetic energy, and all the energy now is in potential energy. And so what you say is the kinetic energy of the ball is all transferred to the potential energy of the spring. It's 1/2 mv squared equals 1/2 kx squared, and then you solve for, what do we look for? X. Cancel those halves, they just go away. 10 kilograms, 5 meters per second squared equals 250x squared. Oh, look, so x is 1. Right? A was the right answer. Is that what y'all put? Yeah. Okay. You'll certainly see some questions like those on the test in another week or so. Is it the week after fall break? Oh, really? Like, what day is it on? Huh? What day is the day of the week? Is that it's a Friday? Oh, let's get shopping then. All right, let's go back to chapter 6. We really just have 2 things in this chapter that we'll see, and that is impulse and how to calculate the force on an object when you know its change in velocity. It's actually a very useful thing to be able to do that. If I can just know an object's change in velocity, then I can know the force that has been used to cause that change in velocity. That's what people do when they study car collisions, that they look at the impulse that has occurred and think about how the velocities of the vehicle have changed. The second thing that we're going to do is look at collisions of particles in 1 dimension or in 2 dimensions and look at how they respond to one another. We'll use the conservation of momentum. So really just 2 things in this chapter. It's a pretty short chapter. In fact, we'll probably get through this chapter and then also get into chapter 7 before the exam. So first of all, we just want to define linear momentum. Linear momentum, we're going to use lowercase p, and it's equal to the mass times the velocity. It is a vector quantity, but you'll see that it's a little easier to deal with than the other vector quantities that we've used. By the way, this comes about, or so I can calculate the momentum. If I have an object with a certain mass, with a certain velocity in that direction, it's just the product of those two. And so our example, let's say that the mass was 1 kilogram and the velocity was 2 meters per second in the x direction. Then we would say that my momentum is equal to 2 kilogram meters per second in the x direction. It is a vector quantity, so it has a direction. So momentum is a vector quantity, not a scalar. It has both a magnitude and a direction. Okay, we'll come back to that. So remember, kinetic energy, on the other hand, we said was a scalar quantity. And so what can we say? Let's say that we have a system of particles that has a total kinetic energy of 0. It has no kinetic energy at all. What can we say about the momentum of that system? Can we say that the momentum is positive, say in the plus x direction? It's negative, it's in the negative y direction, it's 0. Or it could be either positive or negative, but not 0. So if we have a system of particles with 0 energy, all combined up, the particles have no energy at all, what can we say about the momentum of the system? Okay, looking good. Let's stop at 55. 55. Okay, good. C is right. The momentum is 0 because if the kinetic energy is 0, that means they're not moving at all. But what if we said instead of the kinetic energy being 0, what if we said that the momentum of these particles is 0? So I have particles that are all moving around, or maybe not moving around, and the total momentum of that system is equal to 0. What can we then say about the kinetic energy of the system? Is the kinetic energy positive, negative, 0? Or rather, let's make it simpler than that, because you can't really have negative kinetic energy. Is the kinetic energy equal to 0? Or is the kinetic energy not equal to 0? Or can it be either? Zero or bigger than 0. You follow what I'm saying? The momentum of this system is 0. What can you say about the kinetic energy of the system? Either the kinetic energy is 0, it has no kinetic energy, it's not 0, it does have kinetic energy, or the kinetic energy can be either 0 or not 0, bigger than 0. All right, let's stop at 110. 110. Okay, C is the right answer. If the momentum is 0, it's a vector quantity, so it adds up differently from scalar quantities. So I can have, let's see, what did y'all put? Yeah, C is right. I can have, say, if I have this system of particles, I can have this particle moving in this direction, that one in that direction, this one like that. Then the net momentum of this system, adding up the momentum of all the particles, would be 0, because these two would cancel out and these two would cancel out. So when I talk about a system of particles, I talk about their net momentum, all the momentum that they have. And I add it up like vectors, so that it's positive and negative, it can cancel and go away. And so here I could have this system, which has zero momentum, because they cancel out. Or what's another way to have a system with 0 momentum? Nothing's moving at all. So I could either have this or this. So C is the right answer. All right, let's put everything away. We're going to have a little test. So Here, I put everything on. You'll need a calculator. And the form works the same. Make sure you put your N number on the back. And be careful on the back, because notice that there are squares that you don't write in between the squares, right? That if you put space, if you put markings in between the squares, then it'll mess up my grading system. So just try to keep your writing within the little black squares, okay? Y'all ready?
No.
It's on chapter 5. It's not for a grade. It's just for practice. Alright, so treat it like a test. And don't look at your name. I know that we're tied up in here. But I'm not going to count it towards your grade. It's just for practice. Because I want to see sort of where y'all stand on chapter 5. I want you to see where you stand more importantly in chapter 5. Okay. No, it's not fine. It's not really about that. It's practice. It's extra practice. What? Crazy things doing it. All right. All right. Guys, I'm going to keep an extra and I'll shift them all over here. When you get here. 7, 6. You want to make it? Treat it like a test, okay? I'm not going to treat it like a test, but you should. What's up? You have the workbook. You can look at the back. It's the very back page of the workbook. You have about 20 minutes. That's about what you have. It's about a half an exam, a little less than half an exam. So that's about right. Do your best, okay?